Okay, today's lesson is on special right triangles, and these are right triangles where the values get used a lot, and we're going to expand on those values in some future lessons, but right now let's introduce the special right triangles and what we need to know about them. So the first set of special right triangles we're going to look at are ones that have angles of 45, 45, and 90 degrees. And so obviously your 90 degrees would be this corner here. I'm going to mark it with the box, and then the two 45-degree angles would be your acute angles. And since those are the same, there is a geometry theorem that tells us the two legs are the same that they are across from. So this is an isosceles triangle. So instead of 45, 45, 90, you could call this an isosceles right triangle. And in that, we're going to look at some basic side lengths. So if my sides were both 1, obviously they're the same again, and I did the Pythagorean theorem, and you can work that out by hand if you want to. I'm going to give you right now, though, that the hypotenuse would be the square root of 2. So I'm using really simple numbers because I don't want to reduce if I don't have to. And so, again, sides are 1, the hypotenuse is 2. Let's calculate what the sine, the cosine, and the tangent of that would be. So sine is opposite over hypotenuse, and since both of these are 45, I can look at either one I want to. I'm going to look at this bottom one. Opposite would be 1, hypotenuse would be the square root of 2, so I have 1 over the square root of 2, and that means I need to rationalize, so I'm going to multiply by the square root of 2 over the square root of 2. So I get 1 square root of 2 on top, and again the square root of 4 on the bottom becomes a 2, so the square root of 2 over 2. Cosine of 45 degrees, cosine is adjacent over hypotenuse, so my adjacent side is 1, my hypotenuse is the square root of 2. So again, I get 1 over the square root of 2, which is the same thing I just did, so I know that that is going to be square root 2 over 2 in the end. Tangent is opposite over adjacent, so either way I look at the 45, my opposite side is 1 and my adjacent side is 1. 1 over 1 would be 1. So my three important values here are the square root of 2 over 2, the square root of 2 over 2, and 1. And so these are the values you need to know for a 45, 45, 90 triangle. Alright, now I'm going to show you 30, 60, 90 triangles. This is another set of angles that come up a lot, and we need to know these values. And you might be asking why I'm starting out with this kind of triangle. We're going to say that this is an equilateral triangle. All the sides would be the same. That would also mean all of the angles would be the same. So all of the angles would be 60 degrees. Now, obviously that's not 30, 60, and 90. I wanted to show you where a 30, 60, 90 can come from. It can come from putting an altitude down the middle of an equilateral triangle. So let's do that. Alright, so what that does is it creates a 90-degree angle here because it is an altitude, and it splits this top angle into 30-degree angles. And so now if I just focus in on one half of this, I have a 30, 60, 90 degree triangle. So let's keep that in mind. Let's again use simple numbers. Let's say that our original equilateral triangle had sides that were length 2, and I've chosen 2 because when I bisect this bottom one, I can say that this half is 1 and this half is 1. And so that would leave us, since we're focusing on the 30, 60, 90, this yellow triangle here, to find the height of that altitude. And you can use the Pythagorean theorem again. So h squared plus 1 squared would equal 2 squared, or h squared plus 1 equals 4, leaving h squared to equal 3 and h to equal the square root of 3. So I can erase this h here and replace it with a square root of 3 now that I know that. So focus again on the yellow, and let's come over here and do the sine of 30. So 30 is that top angle. The opposite side would be 1. The hypotenuse would be 2. So I have 1 over 2. The cosine of 30 would be adjacent over hypotenuse. Adjacent is the square root of 3. So I have the square root of 3 over 2. And then our tangent of 30 is opposite over adjacent, so I have 1 over the square root of 3. And that one I have to rationalize because I ended up with a radical on the bottom. So I'm going to get the square root of 3 over 3 for that answer. Let me give myself a little bit more room. And for the 60 degrees, now we're going to focus on looking from the perspective of the 60-degree angle, and I'm going to look for sine, which is opposite and hypotenuse. So opposite over hypotenuse gives us square root of 3 over 2. Cosine of 60, adjacent over hypotenuse, gives us 1 over 2. And tangent of 60, opposite over adjacent, gives us the square root of 3 over 1, which is just the square root of 3. Now you'll notice there are some similarities in these. Your sine of 30 is the same thing as your cosine of 60. Your cosine of 30 is the same thing as your sine of 60. They're related because they're in the same triangle, and all that's happening is the opposite and adjacents are switching depending on which angle you're looking at. So those values do end up just flip-flopping depending on the angle, whether you're using 30 or whether you're using 60. So that relationship is an important one to keep in mind. Okay, now we're going to use an application of how we might use this knowledge of special right triangles to help us solve a problem. So our problem is a projectile is launched at a 60-degree angle, and it travels a horizontal distance of 390 feet. How high will it go? Round to the nearest foot. So we are obviously making a triangle, so let me get one of those. Alright, so it's being launched at a 60-degree angle, and I'm assuming that's with the ground. So I'm going to say that this angle down here is our launch angle, and we're launching it from like right here. We're obviously going to have a right angle because we're dealing with right triangles now. And we know it went 300 feet horizontally, and horizontally is our running distance on the ground. So 390 feet this way. What we want to know is how high it goes. So I'm going to call this the height because it actually ends up here. And this would be the height above the ground. So now to use this knowledge to solve a problem, I have to decide, am I using sine, cosine, or tangent? I do that by looking at the angle that I'm looking from and noticing which sides I have labeled. In this case, I have the opposite side labeled and the adjacent side. And if you remember, opposite and adjacent go with tangent. So I'm going to make the equation. Tangent of 60 is h over 390. Now, to put our special triangle knowledge to use, I'm going to plug in the tangent of 60 since I already know what that is from what we did just a minute ago. So that is the square root of 3. So I have the square root of 3 is h over 390. And then to solve the problem, I'm going to multiply both sides by 390 to get rid of the fraction. And that will cancel out over here. And I have 390 square roots of 3 equals my h. Now, you may have problems where they leave the answer with a radical, but in this case it tells us to round to the nearest foot. So I'm going to type that in my calculator, and when I type that in, I get 675.49. And they tell us to round to the nearest foot. Now you could make the argument, because it's a 0.4, we would round down to 675, or you could make the argument, since it's 4.9, that would round to 0.5, and then you would round up. So I'm okay with either way. If you're on a multiple choice problem, it would be very clear. I'm sure that they wouldn't put the two answer choices that close together. So I'm going to be satisfied with 676 as my answer. But this shows you an application of how those values could be useful. Later on in this course, we will get into other more useful situations for these angles. And that concludes this lesson.